Hello everyone, myself is Sriman from CSMD section. Here I am going to discuss about note on the normal form of a spatial stiffness matrix. So if you see the first slide, in the first slide it is there that the normal form of spatial stiffness matrix is a mathematical representation used to analyze the stiffness of a structure in three-dimensional space. It helps in understanding the behavior of a structure subjected to external forces and movements. This normal form provides a concise and systematic way to express the stiffness and properties of a structure. If we go to the next slide focuses on the definition of a spatial stiffness of a matrix. A spatial stiffness of a matrix is a square matrix which relates the displacement vector of corresponding force and moment vector. It represents the relationships between force and moments applied at different points in a structure resulting in the displacement. The spatial stiffness matrix is typically represented using 6 degrees of freedom, 3 translations like x, y, z, and 3 rotations like pitch, roll, and yaw. This slide talks about the components of the spatial stiffness matrix. The spatial stiffness matrix is divided into four blocks: KTT, KRR, and KTR, and KRT. KGT represents the translation stiffness, while KRR represents the rotational stiffness, and KTR represents the coupling between the translations and rotations, and KRT represents the coupling between the rotation and translations. The KTT and KRR blocks are further divided into sub-blocks corresponding to each degree of the freedom. And if we see the next slide talks about the normal form of spatial stiffness of the matrix. This normal form of the spatial stiffness of a matrix is obtained by rearranging the components to simplify the representation. The normal form consists of three submatrices K11, K12, and K21. This K11 represents the translation stiffness, where K12 represents the coupling between translations and rotations, and K21 represents the coupling between the rotations and translations. Then what is a translation stiffness matrix? It is K11. The K11 submatrix represents the translation of stiffness of the structure. It relates translation displacement to the applied forces. This K11 submatrix is a 3 cross 3 matrix and it is also symmetric matrix. The next is coupling matrix, which is K12. This K12 submatrix represents the coupling between the translations and rotations. It relates the rotational displacements to the applied forces. This K12 submatrix is a 3 cross 3 matrix and it is also a skew symmetric matrix. If we talk about the coupling matrix, which is K21, the K21 submatrix represents the coupling between the rotations and translations. It relates the translation displacements and applied moments. The K21 submatrix is a 3 cross 3 matrix and it's a skew matrix. If we talk about the next slide, it is a rotational stiffness matrix, which is K22. The K22 submatrix represents the rotational stiffness of the structure. It relates the rotational displacements to the applied moments. This K22 submatrix is a 3 cross 3 matrix and it is a symmetric matrix. What are the properties of normal form then? Okay, I'll say this. The normal form of spatial stiffness matrix has certain properties that make useful for analysis. The K11 submatrix is a positive definite representing the positive stiffness of the structure. The K12 and the K21 submatrices are skew symmetric, indicating the coupling between the translations and rotations. Then what are the calculations of the normal form? The normal form of the spatial stiffness matrix can be obtained using mathematical transformations. The specific transformation depends on the structure and its degrees of freedom. The calculation involves rearranging the components and simplifying the representation. Then, what are the applications of normal form? The normal form of a spatial stiffness matrix is widely used in the structural analysis and design. It helps in understanding the stiffness of characteristics complex structures. The normal form allows engineers to analyze and optimize the performance of structures subjected to various loading conditions. And what are the limitations in this normal form? This normal form of the spatial stiffness matrix has some limitations in certain cases. It assumes a linear behavior and neglects the effects of non-linearities. Sorry for the disturbance, but let's discuss the limitations of normal form. 1 second, okay? This normal form, the spatial stiffness matrix, has limitations in certain cases. It assumes a linear behavior and neglects the effects of non-linearities. The normal form may not be accurately represent the stiffness of properties of structure with a complex of a material properties. Uh, Conclusion. Before going to conclusion, let's revise what we have discussed in this overall slides. Okay, let's go. Okay. The normal form of the spatial stiffness matrix is a mathematical representation which is used to analyze the stiffness of a structure in this three-dimensional space. Okay, it helps in understanding the behavior of a structure subjected to external forces of movement. This normal form provides a coincides in a systematic way to express the stiffness and the properties of structures. Then, what is the definition of a spatial stiffness matrix? The spatial stiffness matrix is typically represented using 6 degrees of freedom. These translations are x, y, and z, and the three rotations of which roll in it. Remember, when you are writing the spatial stiffness matrix, if it is given as a short answer, write this last one. 1 second, I read it. The spatial stiffness matrix is typically presented using 6 degrees of freedom. The three translations are x, y, and z, and the three rotations are pitch, roll, and nip. First point is the definition, and last point is explanation about the definition. Okay. This is a relationship between forces and movements when they are applied in different points of a structure. Then what are the components in this stiffness of a matrix? The spatial stiffness matrix is divided into four blocks: KTT, KRR, KTR, and KRT. Where KRT represents a translation stiffness, KRR represents a rotational stiffness, and KTR represents a coupling between translations and rotations, and KRT represents a coupling between rotations and translations. Okay, this KTT and KRR blocks are further divided into subblocks corresponding to each degree of freedom. If we go to next slide, then what is a normal form of the spatial stiffness matrix? Generally, this normal form of the spatial stiffness matrix is obtained by rearranging the components to simplify the representation itself. And this normal form consists of three submatrices, which is K11, K12, and K21. Where K1 represents translation stiffness, K12 represents a coupling between translations and rotations, and K21 represents a coupling between rotations and translation rhythms. And we have discussed the translation stiffness matrix, which is K11. This K1, remember, this K11 submatrix is a three-cross matrix and it is a symmetric matrix. This K11 submatrix represents the translation stiffness of the structure. Then next is coupling matrix, which is K12. This K12 submatrix represents a coupling between translations and rotations. And This K12 submatrix is a 3 cross 3 matrix, which is skew symmetric matrix. Next is coupling matrix K21. The K21 submatrix represents a coupling between rotations and translations. The K21 submatrix is a 3 cross 3 matrix and it's a skew matrix also. And if you go to rotation stiffness of a matrix K22, the K22 submatrix represents the rotation stiffness of the structure. The K22 submatrix is a 3 cross 3 and is also a symmetric matrix. Properties of a normal form. Remember, this is a most important step. It will be useful while solving your problems. Okay, the first property is the normal form of the spatial stiffness matrix, which has certain properties that make it useful for analysis. The second property is the K11 submatrix is a positive definite representing the positive stiffness of the matrix. The K12 and the K21 submatrices are skew symmetric, indicating the coupling between the translations and rotations. The applications of normal. This is also one of the important question and which will be useful in your daily life also. While solving the problems. Okay. The normal form of the spatial stiffness matrix is widely used in the structural analysis and design. It helps in understanding the stiffness of the characteristics of the complex. The normal form allows the engineers to analyze and optimize the performance of structures subjected to various loading conditions. This limitation doesn't require because for some problems it may not apply, in which cases I'll discuss whether it is not required or just read it. The normal form of the spatial matrices has some limitations in certain cases. It assumes a linear behavior and neglects the effects of non-linearities. This normal form may not be accurately represent stiffness of properties of structures with complex geometry and material properties. Now let's discuss the conclusion. Okay, the normal form, the spatial stiffness of the matrix, is a valuable tool in structural analysis. It provides a systematic representation of a stiffness properties of a structure in three-dimensional space. Understanding the normal form helps the engineers to design and optimize the structures for various loading conditions. Okay, thank you everyone for listening to my session.